going to be about intensity interferometry. So what is it about? So the idea is to you take two telescopes looking at the same star, and you have to know, so first prerequisite of this talk that you have to know is that typically the stars are unresolved. It means that when you look at the star, even with a big telescope, even with 4-meter telescopes, let's say, for almost all stars, you just have points. So they are not resolved because of even because of diffraction limit given by the size of the telescope. And there are also reasons why they are not resolved. So here the idea is you take two telescopes separated by several meters, and they look at the same stars, and you record the intensity fluctuations of the light recorded at the two telescopes. Or if you don't record a continuous intensity, but if you look at photons, then you record the arrival times of all photons. And then you look at the amount of correlations between the two telescopes. And from that, you can deduce the angular diameter of the star that you wouldn't be able to measure with a single telescope. So how does it work, and why is it not so easy as it sounds? So this is the object of the presentation. So in the first part, I will explain what are the basic physical ingredients behind these intensity correlations of light, and a little bit the history around that. Then in the second part, I will speak about the application of intensity correlations to astronomy. So this is what we call intensity interferometry. And only in the third part, I will present our own work on that topic. So first, the physics of intensity correlations and a little bit the history of intensity correlations. So when you deal with intensity correlations, the basic ingredient is what we call the G2 function, which is so this is the average of the product of two intensities, either measured at different position or at different time, so with a delay or with a distance. And this is normalized by the average intensity. So it's called G2 because one can also define a similar function with the field here instead of the intensity, and in that case, it's called G1. So G2 is, so the intensity is the field squared, so it's the second order correlation of the field or the intensity correlation. So this is useful to study the fluctuations and the noise. And so there is a fundamental noise in light detection, which is always there, which is called the shot noise. It's related to the fact that the light is made of small photons. And the shot noise has some particular statistics. It's a Poisson statistics, and it leads to a white noise. So white noise, it means the same at all frequencies, and it means that it's completely uncorrelated. So if the fluctuations has no correlation, then this function here, you can factorize. So the average of the product equals the product of the averages. And so this function is just 1 at all time and at all distance. And this is the case of a perfect laser. Okay. If now you don't take a perfect laser, but you take light from the stars or from a light bulb, then it's a different situation. So it's what we call an incoherent source or a thermal source, or you can also call that chaotic light. And in that case, you have a supplementary noise. And this noise comes from the wave nature of the light. And I will explain you in detail in the next few slides where it comes from. But what is very important is that this noise is not a white noise, and it is correlated. And the consequence is that the G2 function is above 1. So let's just to be more simple, let's forget about the time. So we take 0 delay, and we look only in the spatial domain. So we look at G2. And the idea is that you look at an incoherent source. And what does it mean, an incoherent source? It means that the source has some size, and it emits with random phases. Okay. So if you take 2 points of this source, then you know it's like a Young double-slit experiment. After propagation, you will get interference of light coming from those 2 points. So it creates some interference fringes. And the distance between the fringes, so the periodicity of the fringes, is due to the distance between the 2 points in the source. Now we have an extended source, and you can decompose that into many couples of many pairs of points. And so you have a complex intensity pattern, interference pattern, which is the addition of all the intensity, all the fringes due to each pair of points. So this is just a hand-waving picture, but this is very useful. So this complex pattern is called a speckle pattern, and you can already think about the fact that the finite size of the source has a consequence, which is that you don't have any infinitely fast fringes inside this speckle pattern, because you don't have infinite couple of points infinitely far away. So you have a kind of cutoff in frequency space if you analyze this pattern, which corresponds to a correlation length for this speckle pattern. So this is not a white noise. Goes from 2 at 0 delay to 1 at very large, at 0 distance, to 1 at very large distance, because at very large distance it's becoming uncorrelated. And the typical drop is made with a typical size, which is called the correlation length. And you can compute the correlation length from the wavelength lambda and the angular size of the source. So L is the size of the source and D the distance. So more formally, you can compute that the G2 function is given by the squared of the Fourier transform of the brightness distribution of the source. But this result, you can really understand it by reasoning in terms of a couple of points and fringes pattern. You have exactly the same phenomena in the time domain. So now let's forget about the spatial aspect, and let's look at the function of the time. If you take an incoherent source, what does it mean? It means that you have a given spectrum with a finite width, and you have a random phase. And similarly, each couple of frequencies inside the spectrum can bit together, and it creates a bit nodes. And if you add up all the possible bit signals between all the different frequency components with a random phase, you get random intensity fluctuation in time. But since the spectrum is not infinitely large, you don't have infinitely fast beating, and so you have a correlation time. It's not a white noise. You have a correlation time, which is given by the inverse of the line width. Of the width of the spectrum. So, and this is the same. The G2 function goes from 2 at 0 delay to 1 at very large delay when it's correlated. And the typical, the characteristical time at which this G2 function drops is given by the coherence time, which is the inverse of the spectrum width. And again, we can more formally compute that the G2 function is given by the square of the Fourier transform of the power spectrum of the source. Okay. So in the 50s, people had the idea of using this kind of property to astronomy. So this is Barry Brown and Twiss, and they were a radio astronomer, and so they first applied this to radio astronomy. They developed a little bit in detail the theory behind it, and then they had the idea to apply that with light. And so they performed a lab experiment first to check if their ideas were correct. And then they made a measurement on the star. So I will show you this paper. So this is really a very well-known paper in astronomy. So here the idea is that with the two telescopes, you can correlate the intensity, compute the G2 function, and if you change the separation between the telescopes, you measure G2 of R. And here you see the amount of correlation, so the G2 of 0, so the G2 of 0 in time, so at 0 delay, the G2 of R, as a function of the distance, and you see the correlation drops. And from the width of this curve, one can deduce the angular size of the star. And you see that you have to separate the telescopes from tens of meters, so about 10 meters, which means that if you would like to resolve the telescope, this star with a single telescope, first you would need to be limited by diffraction and to get rid of atmospheric turbulence and so on. And then you would need a telescope which has a diameter of 10 meters, which is of course hard to do and expensive. So so this technique, this paper was the first direct measurement of an angular diameter of a star.
William, excuse me. Is this a
yes?
Is this a G2 or a G2 minus 1?
This is G2 minus 1 with some normalization. So this is not the true G2 of 0. This is renormalized.
Okay, so it would go something larger than 1 toward 1. Okay.
Yeah, so yes, of course. Yes. So this is G2 minus 1, and then multiplied by some factor, because I will explain that later, that actually with stars you cannot reach G2 of 2. You don't have the full contrast. Okay? Okay.
Yes.
Let me go on. So this was actually a few months before I said that they did a lab experiment, and already this lab experiment, which was published in Nature in '56, triggered some controversy among physicists. And the reason why was that physicists thought about light in terms of photons. And all the explanation that I give in a few slides about this wave noise and so on is really a classical explanation based on interference of waves. But if you think about that in terms of photons, it means that the arrival time of one photon at one telescope is correlated to the arrival time of another photons to the other telescopes. And that seemed really contradictory and hard to understand. So some people claim that it was not possible, that it contradicts quantum mechanics and so on. Some also try to do the experiment in the lab and they failed. Unbarbon and Twist answered, so they analyzed the experiments by the other guys, and they understood that the other experiments were not sensitive enough to see the effect. And then it was understood by Purcell and by Unbarbon and Twist themselves that this G2 effect, that this excess of correlation, which we now call the HBT effect from Unbarbon and Twist, is actually due to the so it was said clumping at that time, but now we say bunching of bosons. So it's related to the fact that light is made of that photons is made of bosons, and then if you take into account the quantum statistics of bosons, then you can understand again this bunching effect in the framework of quantum mechanics. Around the same time, the laser was invented, and the laser, as I said, behaves differently. And so all this was really a bit complicated to understand, and this led to the development of the quantum theory of optical coherence by Glauber in '63. And if you go to the Nobel speech of Glauber, he really emphasizes the fact that the HBT experiment was really a key in understanding all that. And one can consider that the HBT experiment was really the birth of modern quantum optics. And in all quantum optical labs, G2 functions and correlation functions are still used to characterize the quantum sources and so on. So this is really a very important effect in the framework of quantum optics. But in the rest of the talk, I won't speak about quantum optics anymore. I will speak about the applications to astronomy. But I can ask questions now if you have questions on the first part. I don't hear anything, so it means no question. Okay. So, okay, so after this first demonstration, Unbeilborn and Twiss, so Unbeilborn mainly wanted really to use that technique on a larger scale to now measure the angular diameters of many stars, because it was really a new possibility. And so he moved from England to Australia, probably because the weather was much better there. And he built with collaborators a dedicated observatory at a place called Narrabri. So they put two very huge light collectors, so with diameters of 6.7 meters, on a circular trail, which could allow them to use distances almost as long as 200 meters. So which is a huge spatial resolution. And it also allowed to orient what is called the baseline, which is the distance and orientation of the two telescopes, which allowed to follow the star during the night with a constant distance. And with this observatory, they were able to measure the angular diameter of 32 bright stars. So they built the first catalog of angular diameter, and then they study also some binary systems, light having emission lines, and so on. So this was a huge breakthrough for astronomy and for stellar physics, because if you combine the measurement of the angular diameter with other measurements, for example, spectroscopy, when you can deduce the temperature, and photometry, and so on, then you can really determine all the physical parameters of the star and study or compare the measurement to evolution of stellar physics, to model of stellar physics, and so on. So this was really a breakthrough for astronomy. And then in the 70s, intensity interferometry completely stopped. So they stopped the observatory, and this was not used anymore until in the last years. So one has to understand why. And the big issue of intensity interferometry is that the signal to noise ratio is very poor, which means that the sensitivity is very poor. And so what they did in the 70s is that they measured the 30 most intense stars, so the most the most brilliant stars. But after that, it was too hard to measure fainter stars. So it means that you need very long integration time, very large collectors, and that it's limited to the brightest stars. So why is that? Why is it so bad? So the main point is that the spectrum of the stars is, of course, very, very large, which means that the coherence time is very small. So if you don't filter the light, if you have white light, then the coherence time would be femtosecond, and there is no way to measure that you can measure anything. So what you have to do is you have to filter the light. So for example, if you take a filter with a bandpass of 1 nanometers, then the coherence time is increased to about 1 picosecond. So the two consequences of that is that first, you throw away most of the light. And second, even 1 picosecond is still too fast for the electronics. It's still too fast for the timing resolution of your detector, even now. So it means that the G2 function that you measure is not going from 2 to 1. With a characteristical time given by the coherence time, it's going to be convoluted by the electronic response of your equipment, of your detector, which means that this G2 function, this bunching peak, if you want, will be smoothed over a much broader size given by the electronic time resolution, and the consequence that the amplitude will be also much smaller. So the contrast, which is what we call G2 minus 1, so this is what we call the contrast, will be reduced to a small value given by the ratio between the coherence time and the electronic time. Okay, and so you will have to measure a tiny bunching peak over a large background, because the background here stays at 1. So to be able to do that, you need to accumulate a lot of statistics, a lot of photons, but you threw away most of the light. So it's hard, okay? And you have to accumulate for a very long time, or to use very large collector to have as much light as possible. So that's the big issue of intensity interferometry. And in the 70s and even more in the 80s, there was another technique which started to be developed, which is direct optical interference, or we also call that amplitude interferometry or Michelson interferometry. And the idea then is you really combine, you collect the light of the two telescopes, and instead of having two detectors in the telescopes, you really combine the light and make the two lights interfere together in optical fringes, and you look at the contrast of the optical fringes. And you get the same information as with the G2 function. You get the mutual coherence between the two telescopes, which is also related to the angular size of the star. So it's similar kind of information, but you can really see the interference fringes in real time. You don't need a very narrow filtering. In principle, you know that interference in white light is possible if you have no delay between the different paths. So you can have full contrast. You're not limited by any timing resolution of any detector. And so you have a much, much better sensitivity. Of course, this has a price, which is that you need first to recombine the light together. And if the telescopes are separated by hundreds of meters, this is very hard. And you need to control the optical path at better than lambda if you want to have stable interference fringes. So it means that you need very high quality optics. You need to compensate for atmospheric turbulence. So this is what we call adaptive optics. You need optical delay lines, which have to be controllable and actively controllable, because when you are observing a star in the sky, the star is moving in the sky, and so the delays between the two optical path on the telescope is changing always in real time, so you have to compensate for that. So this is very, very hard. So you can do that only with a very complex and expensive facilities with tens of engineers working all together to make the thing work. So there are only a few such interferometers in the world. I've put some picture here. So maybe the most known is the VLTI in Chile. So it means a very large telescope interferometer, where they can use either the 4 big telescopes here or the 4 small telescopes. And there are 2 other interferometers in the US. One is called CHARA with 6 1-meter diameter telescopes, and this one I think has 4 telescopes, also in the US. But they are the only interferometers in the world. So this is a very complex technique. So just to summarize the difference between amplitude and intensity interferometry. So amplitude interferometry is very efficient because optics does the job very well of detecting interference. And it is also hard because optics sets the required precision, which is lambda. And so that's very demanding, and in particular, it's more and more demanding when you increase the distance between the telescopes, if you go to fainter star, or if you go to shorter wavelengths. And for example, the VLTI here works only for wavelengths above 1 micron. So it works only in the infrared. It means that there is no interferometer in the southern hemisphere which is able to work with visible light. And of course, you don't always have the same stars in the southern hemisphere and in the northern hemisphere. So this is a strong limitation. And intensity interferometry is not efficient because electronics does the job poorly of detecting those fast optical correlations. But it is also easy because electronics sets the required precision. And for example, if the electronic timing resolution is 100 picosecond, it means that you need to know your optical path only at 3 centimeters, which is relatively easy. It means that it is insensitive to turbulence. You don't need a very good optical quality for your telescopes. You don't need adaptive optics. And of course, electronics also allows many other things like post-processing. So you can record all the photons at all the different places and then compute the correlations afterwards. So for example, this is what has been done, in the radio waves for making a picture of a black hole. You heard that maybe 1 or 2 years ago. So with all radio observatory spread around the Earth, and you could put everything together and do post-processing. So this is the kind of things that you can do with intensity interferometry. So there is now a revival of intensity interferometry in the astronomical community for several reasons. So first, of course, the detectors and electronics, they made progress since the 70s, so we can now have much better sensitivity. And as I said, we have new technologies now, like GPS, atomic clocks, telecom fibers, etc. So all those kind of technologies can be used to synchronize different telescopes at long distance or transfer the signal, etc., which allows really to use to go to kilometer distances between telescopes, which allows to increase the spatial resolution that you can get. Also, the progress with computers allows to record all photon arrival times and do post-processing. So with all those, one can really envision to build telescope arrays of over kilometers. And what triggered the revival of intensity interferometry is that those telescope arrays, they are actually being built. And for example, so not with optical telescopes, because that's too expensive, but with Cherenkov telescopes. So Cherenkov telescopes are crude telescope made for looking at Cherenkov radiation in the atmosphere. So it's for gamma ray astronomy and cosmic ray and so on. So they are of poor optical quality, but this doesn't matter for intensity interferometry. And for example, there is one facility which is now being built in Chile, which is called the Cherenkov Telescope Array. And it will be made of 99 telescopes spread over 4 kilometers squared. So, and the biggest of them, so not all of them will have the same size, but the smallest will have a diameter of 4 meters, so they are shown here, and the biggest, shown here in the background, will have diameter of 23 meters. So they are huge telescopes. And if you have an array of telescopes, each pair of telescopes is measuring, and you do intensity interferometry, it measures, it gives you access to one Fourier component of the image of the star. So if you have an array of telescopes with all the correlation, with all the mutual pairs that you can have, you can really think of rebuilding a picture of your source and see maybe star spots or small details. And also, we have some ideas to improve the sensitivity, for example, by running many multi-channel measurements at the same time, for example, using wavelength multiplexing. And intensity interferometry can also be useful for some more specialized experiment, like the study of narrow spectral lines or polarization reserved experiment and so on. So for all these reasons, there has been a strong revival in the community with two different approaches. So either with Cherenkov telescopes like this, and last year and recently, two consortiums demonstrated intensity interferometry measurement with this kind of telescopes. So the MAGIC array in Spain and the Veritas array in the US. And some other groups are working towards intensity interferometry with optical telescopes. So of course, with optical telescopes, you don't have 99 telescopes and 23 meters telescopes, but you can design instruments that you can adapt to existing telescope, existing facilities. So for example, to the VLTI. So this is another approach. And this is in this approach that we are working, and I think we are currently the leader on this approach. So I can also take questions now before entering into the details of what we are actually doing.
William, yes, just for curiosity, so you mentioned this adaptive optics to correct. So can you hear me well?
Not very well, but yes, you are speaking about adaptive optics?
Yeah, what is the general concept? But probably, of course, you mentioned you have to take into account turbulence in atmosphere and this kind of things. Is there a general principle to explain what is this adaptive optics, how you clean the signal?
Yes, okay. So the idea of adaptive optics, so I'm not at all a specialist, but I know a little bit. The idea is that you can measure the wavefront of the light. So for example, you look at some small object in the sky, and you look in the field of view, you have another brighter star somewhere. You take the light of this brighter star, and you send it into a wavefront analyzer, which will analyze the distortion in real time induced by the atmosphere. And you can retroact, you can use this measurement to make a feedback on the telescope itself. And for that, you need, in the optical path of the telescope, you need some movable mirror. So how do you say? So a mirror which is segmented with 100 or 1000 pixels, which can move. And so you can compensate the wavefront in real time. The wavefront, which is distorted by the atmosphere, you compensate it in the real time with a special mirror. Does it answer the question?
Yeah, it does. Thank you.
And you don't need to do that for intensity interferometry, but you need to do that for direct interferometry, because the delays induced by the refractive index in the atmosphere, they are larger than lambda. So it's important to compensate them.
I see.
I have a question.
Yes.
I would like to know if you have some ways to differentiate between the quantum and the classical correlation in these telescopes.
Between classical correlation and what?
And quantum. Can you differentiate? Yes.
Yes. So if in the telescope we correlation function and without any bunching, then we can claim that either our experiment is not working properly, or that the light is coming from a laser and not from a star, or that starlight is coherent. So it's not really classical versus quantum. It's coherent versus incoherent light. Now, if we measure an anti-bunching, so a G2 function which goes below 1, then we can say, oh, maybe there is a form of intelligent life sending us a single photon one at a time. So we have some quantum source in space.
Nice, thank you.
Oh, William, sorry, to understand better, so if you have 99 telescopes, 99 measurements, and you do cross correlations, so you can typically image your system with something like 99 pixels. Is it
no, because if you have, let's say, 100, it's simpler. 100 telescopes, then you have 10,000 pairs of telescopes. So you have 10,000 points in the Fourier space. So it's not so bad.
Okay. Yeah, no, okay. So it's actually not redundant.
Depending on where the telescopes are, you may have some redundant values, of course. So if you have an ordered array, you will have a lot of redundancy.
Okay, that's okay.
Because that's the distance between the telescopes which matters. So if it's too ordered, then you have a lot of redundant pairs.
Okay, so it
And
scales
actually you have more points than that, because as the Earth rotates, actually what matters is the projection. So the star that you look is never exactly at the zenith; it has some angle, and so this is the projection which matters. And so the in time, so you also explore several points in the Fourier space during one night.
Okay, oh, very good. Okay.
Okay,
Other questions? Please.
Okay, so let me go on with our specific work in Nice. So we are actually a bunch of people. A part of the team consists of physicists initially cold atom people like me. And so we are developing all the instruments and all the lab calibrations and so on. We are interacting a lot with astrophysicists and astronomers who also have access to telescopes and who give us ideas of which stars to look at because we know basically nothing about stars. And we are also working with other people also in the Nice area who are specialists of timing metrology, so transfer synchronization at long distance and so on. So I will present you the first version of our instrument. So now it has a little bit evolved, but the principle is the same. So the idea is really to develop a very small instrument that is transportable and that can easily be put at the focus of the telescope. So the light is coming from the telescope from the left. And we have a very compact instrument where the first ingredient is a dichroic beam splitter. So it's just to send a part of the light to a camera just to help us align everything and to follow the star during the night. And on the main path, the light is filtered. So with this, to increase the coherence time, as I said, we need to filter the light. And also we need a polarizer to select one polarization component. And the light then is focused and injected into a multimode fiber, which allows to have the rest of the equipment in another room a bit later and not directly at the focus of the telescope. So in this part, we use a filter with 1 nanometer bandwidth, as I said at the beginning, with a wavelength of 780, and it gives a coherence time of 1 picosecond. One very important ingredient is the photodetectors that we are using. So you might know that photodetectors have dead time, which means that after detecting one photon, it cannot detect another photon for several nanoseconds. So to overcome this limitation, the standard method for HBT experiment is to split the light into two paths and to make the cross correlation between two detectors. For technical reasons, we have to introduce some delays here, but it's a detail. And so the detectors that we are using have temporal resolution limited by the jitter of the detector. So it means that when a photon arrives, the photodiode will trigger a signal, but with some delay, and this delay has some jitter, some uncertainty, so it's not the same. And this jitter limits the resolution of our whole instrument to about 500 picoseconds. And then the electronic pulses produced by the detectors, they are recorded by what we call a time-to-digital converter, a TDC. And from that, we can compute the correlation function. So as I said, the contrast of the correlation function, or what we call the bunching peak, will be reduced to the ratio between the true coherence time and the jitter of the detector, which will be 0.2%, 0.2%. So this is going to be small signal. We can test everything in the lab by just taking a light bulb, injecting that into a single mode fiber. So it simulates spatially coherent source, but with an incoherent spectrum. So it's actually like an artificial star. It's like an unresolved star. And with this setup, we can measure a G2 function, which goes, so we see the bunching peak, and the amplitude is indeed 2×10⁻3. I won't enter into the details because it's a bit technical, it's a bit of black magic, but to be able to obtain this kind of function, it's not so obvious, and in particular, one needs to get rid of any kind of spurious correlations that might appear due to electronic problems in the photodiodes or in the TDC or elsewhere. So it's not so obvious to have this background here, which is as clean without any spurious correlation. So now it works. Let's go to the observatory. So we are very lucky. So this is a
We lost William, or?
I think so. I cannot hear.
Okay. I thought it was my connection was failing. But... Okay. Que é acha que a internet no Brasil era o internet europeu.
Ironicamente, quando ele chegou em Nice, pertinho dele, caiu a conexão, né? Ele estava falando de tanto telescópio longe.
Mas quem está sediando? É você, Roman? Você que está sediando a reunião?
Eu estou sediando, mas eu acho... Sim, mas acho que não importa. Tipo, se a minha
Não importa, né?
cai,
Eu sei que no
a
Zoom
reunião
importa.
continua.
Eu sei que no Zoom importa quem é o host.
Eu acho que aqui... Não, espera.
Acho que...
Alguém entrou. William. Welcome back, William.
okay. So I'm sorry. It seems like I lost my connection.
Mm-hmm.
Do you now hear me and see me well?
Yes. You just have to activate again your presentation.
Yes. Where is it? Here.
But it was good. Brazilian people have a very bad opinion about their internet connection. And now we feel a bit better.
Yeah, it can happen everywhere.
Yes. It's good to know sometimes. It happens everywhere.
Okay, do you see everything? You see the presentation?
Yes.
Okay. So I don't know exactly when it was cut. So I was probably at this slide. Is it correct?
No, at slide 27. The map of the region of Nice.
Okay.
Yeah.
Okay. So the observatory is 45 minutes from our lab, which is located here. And this is a really nice place. So this is on a plateau at 1,300 meters. So the small white buildings that you see are the facilities of the observatory. And more specifically, we used a lot the two telescopes which are in this building called C2PU. It's a dedicated infrastructure for research and training. And so in this building, we have two telescopes separated by 15 meters with a diameter of 1 meter. So for me, it's already a large telescope, a big instrument. In the astronomical community, it's a small telescope. But this is already very nice to have access, to have an easy access to those telescopes. And so here you see the focus of the telescope and the instrument that we put directly at the focus of the telescope. So here I have a close up. So here in this box, we have the plate that I was talking about, which send light, part of the light on the camera. And here, the light which goes through is focused on a fiber. And here we have the filters and the polarization filters that are necessary to increase the coherence time. So the fiber is a multi-mode fiber with a diameter of 100 microns. Because of turbulence effect, it would be very hard and very inefficient to try to inject the light in a single mode fiber. So the whole setup is really very small without any moving part, which means that to optimize the injection of the light in the fiber, we use the whole telescope itself. Of course, the whole telescope can be moved to point very precisely at the star. But for me, who is used to work with mirrors and so on, small mirrors and so on, it's very impressive to think about the fact that we will inject the light in the fiber with an instrument which weighs more than 3 tons. Okay, so this is the first measurement that we did in the observatory and at the telescope. So the first experiment that we did was with only one telescope, so which means that there is not any spatial separation between the two intensity that we measured. So this is G2 of tau. Maybe I didn't forget to mention it, but we work in the photon counting regime, which means that the detectors, they count photons one by one. So it's not the continuous intensity regime like it was for on-by-one and TWIS. And here, this is 3 correlation function measured on 3 different stars. So of course, we have chosen very bright stars. And so we see very clearly the bunching peak, which goes to about 0.2% as expected. And for those measurements, you can see the observation time written here, so it's a few hours. So all this is perfectly consistent with our lab test and our lab expectations. And of course, we don't learn anything except that the stars are not lasers. Okay, but there is no more relevant information. It's just a technical test that all our experiment is working well in real conditions, which means with turbulence and so on. So after that, we duplicated our setup and we used the 2 telescopes simultaneously. So here we don't need to split the light into 2. We just put 1 photodiode at each telescope. We have to take care of the delay here, which is introduced by the fact that the star is not at the zenith. And so there is an optical delay here. So what we are doing, so the TDC is actually able to compute the G2 function in real time, and that's much more efficient than recording all the photons and doing it afterwards. But we need to take into account this variable delay. And this varies actually quite fast because of Earth rotation. And so what we did is we record the G2 function every 10 seconds. And at the end of the night, we can sum up all the G2 function, or average all the G2 function which are measured but before averaging, we introduce a small delay, which we compute from the knowledge of the star coordinates and the telescope coordinates. The astronomers, they know how to compute that very well.
Sorry, can I interrupt?
Sorry?
Can I interrupt? Can I ask a question?
Yes.
You are recording G2 at every 10 seconds. This is like a cross grain.
Yes.
This is like, and why? Why not directly? Why are you measuring G2 at every 10 seconds? Why are you doing this kind of cross graining?
we record like this, but we average during 10 seconds. And then we have a G2 function, which is very, very noisy, so we don't see anything. And at the end of the night, I mean, those G2 functions are average for several hours, okay? So what we do here is that we average only for 10 seconds, and then for another 10 seconds, and then for another 10 seconds. And before averaging all those elementary G2 function, we have to shift a little bit the time axis to take into account the delay here. And then we have an average over also several hours. But if we don't take into account this small delay, this variable delay, the bunching peak will be smoothed out over such a wide range that we won't be able to see anything.
Oh, so this is to overcome the noise.
No, this is to overcome, to compensate, to be able to compensate for the variable delay here. Because we need to overcome the noise, that's true. We need to integrate for a very long time. So in 10 seconds, it's not enough. We need hours. But if during hours, the delay here is varying a lot. And so to be able to average during hours without having the problem of this variable delay, we just make many pieces of 10 seconds.
Oh, okay. Yeah. Thank you.
So,
okay.
Basically, sorry, can I just?
Yes.
So every 10 seconds, I mean, the optical path between the two telescopes started to change substantially, and so
a few picoseconds. In 10 seconds, it's a few picoseconds. So it's negligible compared to our resolution, which is about 500 picoseconds.
Okay. Mm-hmm.
Yeah. So William, just one question, since we are asking questions now. So could you go back one slide? So your signal is, okay, it's 10 to the minus 3, right? So you can identify the bunching, but even after you treating your data, you can see that G2 goes below 1 at the same order, 10 to the minus 3, right? So how is that a way to show? So you just have a factor of 2 to differentiate a peak and one thing that goes below, and the valleys that go below 1, right? So how can you? I mean, I know that this is after statistics and you're cleaning up the signal, but do you get signals sometimes that go even below the point, the 10 to the minus 3? I mean, that is comparable to the bunching peak. Do you get values that are below? Because this is G2, right? And it's not the contrast. It's really G2, right?
Here, yes. Well, so you mean so here sometimes we have noisy peaks going below 1. Yes, that's true. But the more we integrate, and the more those noisy peaks disappear, while at the center it stays there. So it's just a question of signal to noise ratio.
Yeah, which is a factor of 2, right? I mean, if you see the C, the Pollux case, sometimes I'm not sure. Do you get values that are comparable to the central peak? So the signal to noise wouldn't be the most amazing value, right? So
you mean, do I have somewhere later on the curve another peak which could also be as high as this one?
Yeah, more the valleys. So my question is more, okay, the bunching has a good interpretation. You have the bunching, you have the peak. But what about the valleys that are appearing in your noise? Sometimes they are comparable to the size of the peak. So that's what I was trying to understand. What does it mean to have valleys that are so?
Okay, so it means either that we didn't integrate long enough, or that we have some spurious correlations that we did. So it's just only technical stuff. So of course, in all the data that we present, we made sure that the bunching peak was significantly higher than all other noisy peak or artifacts. But it needs some integration time, and it needs some work to remove spurious correlations. But if there were some real physical effects with strange things, then that might be interesting. But so far, it's just a technical noise.
Okay.
Okay. Okay, so this is the two telescope experiment. So this is examples of data taken with the two telescopes experiments. So in the two telescope experiment, you have to take care to look at a star which is small enough. So if the star is large enough that with the 15 meters separation you resolve them, then the bunching peak will disappear. So we have to look at stars which are bright enough and small enough in angular size. So, for example, we looked at those two stars. We see clearly the bunching peak. And if we, so of course, those stars, they are very bright, they are very well known, so they are already measured by many times. So we know their angular diameters, and so we can compare our measurements to what would be expected. And so if we have zero delay, this is what we can calibrate in the lab. We have given certain value for the bunching peak, which is here. So here it's not the contrast, it's the area of the bunching peak for some reasons that I don't want to explain. And we can compute what is expected for the G2 function for those two stars. And you can see that we already see a very slight reduction of the bunching peak because of the finite size of the star, and it is, I mean, the measurements lie well in our, so within our error bars with what is expected. Okay, and so after that, we did a third experiment by looking at another star, a fainter star, which has a very, very strong emission line. So we changed our wavelengths, and so we looked at the H alpha emission line at 656 nanometers. So this is a spectrum of the star with a which is normalized to 1 in the continuum, and here at the emission wavelength, you see it goes 20 times above the continuous background. So this is a very, very strong emission line. And so by setting our filter just around this emission line, then we have much more light than what would be expected just from the average magnitude of the star. And in that case, the coherence time is not related to our filter, but is really related to the emission line of the star. So in principle, G2 of tau gives us information on the spectral width of the star, of the emission line, and G2 of R gives is related to the size of the emissive region of this emission line, which is not the photosphere itself of the star, but circumstellar envelope. So this is the measurement of G2 of tau with one telescope, and thus these are the two measurements for different separation between the telescope, different projected baseline with the two telescope experiment, and you see the strong reduction of the bunching peak. So from that, so actually from the spectrum, so after that we collaborated with astrophysicists developing models of stars. And by using the spectrum, which is showed here, so not only, so this was the H alpha emission line, but there are many other lines. They can fit all their parameters. So of their stellar model, there are many parameters, but they can fix them by comparing to the spectrum. And once the parameters are fixed, they can really compute the physical size of the star. And since what we are measuring is related to the angular size of the star, we can deduce the distance of the star. And so this is an adjustment of the G2 function, so the amplitude of the G2 function. So this is called the visibility in astronomical terms. And these are the two measurements. The profile here is related to is computed from their model. And the global width of this curve can be adjusted with only the distance of the star as the free parameter. And so this measurement allowed us, although our error bars are not very small, to get an estimation of the distance of the star, which is comparable in precision with what was already known by other methods. And so if we combine our measurement to the previous measurements, we can refine very slightly the distance of the star. Okay, so this was just an example to say that we can also measure something, which is not only a technical proof of principle. Okay, so I am coming to the conclusion. So what we have done so far is to show that we're able to measure the spatial correlation function with two separated optical telescopes, which is actually the same as what HBT did a long time ago, but now we did that with modern technologies, so photo counting detectors, optical fibers, and so on. And we reached a leading position in the revival of intensity interferometry with optical telescopes. Beyond that, we have applied already the technique to stars with strong emission lines. So I have shown you the measurement made on P Cygnis distance. We also had a one-night observation in child on the 4-meter telescopes, and we looked at some exotic star called Eta Carinae. And this is a picture taken from the webcam looking at the telescope, and the very small guy here is myself, is me. And more recently, this year, we did some other measurement runs on two other stars, Rigel and P Cygni, again this August, and this is not analyzed completely yet. So what comes next is we would like to use a third telescope on the Callian Plateau and perform a 3-telescope experiment, which would be the first one with optical telescopes that we do intensity interferometry with more than 2 telescopes. We also want to test a new generation of detectors, which have been developed for the field of quantum optics. So there are single nanowires, single superconducting nanowire, single photon detectors. Which have a better efficiency and a much better temporal resolution. And so I think this is really the future for this topic. And we have ongoing discussions to go on the VLTI site in Chile. So of course, not on the big telescope first, but at least on the small telescope as a first test, and then first with 2 telescopes, and then with 3, and then maybe we'll have in some time access to the big telescopes. Of course, all the telescopes in Chile are closed since March, so this is going to be delayed. Yeah, so I thank you, and I finish with a picture taken at Callian. So maybe you heard about the Neowise comet, which was visible recently. So this is a picture of the comet, and here are the 2 telescopes that we are using. And if some of you know a little bit the sky, you may recognize other things on this picture. Thank you very much.
Thank you. Okay. So, are there some questions? So I was wondering, William, so right now, it's this the response time of the electronics that makes that you are punching that is quite low of the order less than 1%. Okay, so
Yes.
what is the typical gain that you expect with this new generation of detectors and electronics? Is it like a factor 10, a factor 2?
Okay. So the best SNSP, so the best resolution which has been achieved with SNSP is on the order of a few picoseconds, like 2 or 3. One problem is that it's also the case for avalanche photodiodes, actually. So the avalanche photodiodes that we have are not the best ones in terms of timing resolution, but it's the best trade-off between the timing resolution and the active, the surface of the active area of the photodetectors. And since we are not able to use single mode fibers, but we need to have multimode fiber with some diameter to inject efficiently the light, we cannot use the smallest detectors available. So we cannot use the better resolution in terms of timing, the better detectors in terms of timing resolution. So what we have is a good trade-off. I think it's the best trade-off in for the available, commercially available avalanche photodiodes. And for SNSPDs, it's a bit the same problem. So the commercial ones which are available so far, they are made for single mode fibers. And we are discussing with a group, a research group, which built their own detectors, and they also have a spin-off company selling them and so on. And very recently, they were able to make detectors with also 100 microns active areas, and the resolution is on the order of, let's say, 50 picoseconds. So it means a factor of 10 better than what we have, and a factor of 10 better on the timing resolution directly means a factor of 10 shorter observation time for the same signal-to-noise ratio at the end for the same star. So, and a factor of 10 in the observation time is a huge, a huge improvement, because so far we are really limited by that. So with just one night of observation, we can only look at the very brightest stars. And for example, we would like, for the free telescope experiment that we would like to do in Calern, so the third telescope is separated by 150 meters. And the problem is that if you want to still have some correlation with this distance, you need to find a star which has a very small angular diameter. And if it has a very small angular diameter, very probably it's because it's farther away from us. And if it's farther away, then it's not so bright. And so you cannot find a star which is both very bright and with a very small angular diameter. And so far, the best stars that we identified for this 3 telescope experiment, it would need 80 hours of integration time, and which is not really reasonable because the telescopes are also used for something else. And if we have those new detectors, and if we can win a factor of 10 in the observing time, then 1 month of observation turns into just a few days. So it's a huge improvement.
Okay.
I have a question. Have you considered the effects of gravitation in these studies?
You mean, does the gravitation field change the G2 function or things like this? Or
Yeah.
so the answer is no, because we don't think there is any effect like this.